What happens when you scatter magnetic and non-magnetic ions randomly through a crystal, yet find no magnetic order even near absolute zero? BaCu₁/₃Ta₂/₃O₃ is a three-dimensional perovskite where disorder creates not chaos but a uniquely bounded quantum singlet ground state. Let's start by examining how the crystal structure itself constrains the magnetic landscape. Building on that structural foundation, synchrotron X-ray diffraction reveals a tetragonal perovskite where copper and tantalum randomly share B sites. Yet EXAFS data uncover crucial local ordering. Each copper is surrounded predominantly by tantalum neighbors, suppressing extended copper-oxygen-copper networks and preventing large magnetic cluster formation. This local chemical order directly shapes how spins interact across the lattice. These structural constraints translate into a broad but bounded distribution of antiferromagnetic exchange interactions. Multiple exchange pathways create distinct peaks in the distribution: strong direct copper-oxygen-copper coupling near 70 K, intermediate paths with one intervening tantalum near 4 K, and weaker long-range exchanges near 0.1 K. Yet crucially, the distribution never vanishes. Now let's examine what this bounded disorder looks like in measurements. Turning to experimental evidence, magnetic susceptibility shows a characteristic power law divergence below 10 K, with no trace of ordering or freezing. Meanwhile, specific heat exhibits a broad Schottky anomaly and transitions to linear temperature dependence at the lowest temperatures, with 60% of magnetic entropy still recoverable at 0.1 K, confirming a highly dynamic quantum singlet network. These observations distinguish this system from conventional random quantum magnets. In contrast to the infinite randomness fixed point predicted by strong disorder renormalization for many random magnets, BaCu₁ exhibits finite randomness. The structurally constrained disorder prevents the scale-free exchange distribution and associated thermodynamic singularities, instead producing a ground state characterized by a bounded distribution with multiple energy scales. Quantitatively, a distributed exchange dimer plus orphan model captures the full thermodynamic landscape. The model treats the majority of copper spins as forming antiferromagnetic dimers, whose strengths are drawn from the reconstructed exchange distribution, while a small fraction of orphan spins accounts for the residual paramagnetic behavior, achieving remarkable agreement with all experimental data. These findings open new directions for engineering quantum disordered phases. This work establishes a new paradigm. Structurally constrained randomness can engineer quantum spin liquid, like ground states, without requiring geometric frustration. Despite copper site occupancy above the percolation threshold for cubic lattices, no magnetic order emerges because local chemical order shapes the energy landscape, suggesting a versatile route to three-dimensional disordered quantum magnetism in other oxide systems. BaCu₁/₃Ta₂/₃O₃ reveals how randomness, when architecturally bounded by local order, generates a stable quantum singlet network, neither frozen nor ordered, a controlled disorder pathway to exotic magnetic states. Visit emergentmind.com to explore more cutting-edge quantum materials research.